I'm working in a research project that considers cracks or defects in high temperature steels of the 9% chromium range. And we have welded joints here from two base materials with another buttering layer, and where we were wondering how to calculate a C star integral. So if somebody doesn't know what a C star integral is, it's basically a parameter in order to quantify the crack tip loading under steady state creep. So now I can't. Okay, thank you. What's better about these steels? So these 9% chromium steels, like I said, okay, doesn't work at all. They are common choice for power machinery components with operation temperatures of up to 650 degrees Celsius. So it's a typical, application range where creep plays a major role. And if you're having huge components like turbine housings of gas turbines, these weldings often have to be made at place, and therefore there's no heat treatment of the whole component possible. So there's only a small available area for heat treatment, and also should be repairable. And therefore, if we are welding, we can obtain a homogeneous microstructure in the weld. So on the bottom line, you can see EBSD mappings of a comparable welded joints. On the left-hand side, you can see the base material. On the right-hand side, you can see the weld material. And the heat affected zone is it in itself very inhomogeneous as well. So we have a coarse-grained heat-affected zone caused by the high temperature and low cooling ranges next to the weld material. In the middle, there's a fine-grained heat-affected zone that is formed because the precipitates do not dissolve at these temperatures where we have here. So a relatively fine-grained zone is formed. And to the left, so to the base material, next to the base material, there's a intercritical heat-affected zone. And this heat-affected zone consists of partly dissolved microstructure and over-tempered martensite. And if you're looking at the creep properties, so this is just a schematic drawing we obtained from literature data from a former colleague of mine, fitted to the so-called Norton model. So the Norton model is a power law model that is used in order to describe the minimal creep strain rate as a function of the stresses. So it's comparable to the Ramberg-Osgood model, but as a rate formulation or a strain rate formulation, if you plot it in such a double logarithmic diagram, you get straight lines. And as you can see, we have here the three heat-affected zones that were all for itself microstructurally simulated. So they were heat-treated from base material, the P92 in this case. The y-axis component, what translates to the A, as well as the slope, what translates to the N, differ greatly. And therefore, you are asking, does this play a role if we want to calculate the C star integral? And if we want to calculate the C star integral for specimens like the CT specimen, that's a pretty common fracture mechanics specimens, there are standards like, for example, the ASTM E1457 standards that provide formula to calculate C star from the load line displacement rate and the forces for different geometries. And it also covers welded joints. But these welded joints are only approximated as bimaterials of the base material and the weld material. As you have seen, we don't only have a base and weld material, we have another buttering layer and three heat-affected zones that are for itself, not homogeneous and therefore considered as three subzones that are all not covered inside this formula given in the ASTM standard. And additionally, the Norton exponent must be constant or identical for the whole specimen. And as you have seen, we have build a finite element model, one would can assume you can also calculate the C star integral. So it's basically derived from the J integral, but as a rate solution, considering the strains as strain rates, and therefore you can also calculate a C star integral or a CT integral for times to infinity in abacus. But these integral formulations are strictly not valid for inhomogeneous materials, and therefore for such a welded joints like we have here, both common methods in order to calculate the C star integral are not directly applicable. So a third method is a power approach. So like for the J integral evaluation, where you can consider the difference in potential. So the difference if you have two different crack configurations, you can consider the difference in the stress power, what itself is the time derivative more or less, and therefore you can do a finite element solution for a crack length A and a second crack length that is incremented by delta A, and obtain these force over load line load line crease displacement rate curves, and the area in between these curves, so it's pretty small as you might imagine, gives you a direct C star integral with the surface that got freed by extending the crack. So what I did was I, as you've already seen, built a finite element model of the configurations I'm actually testing in the lab right now. So we have the P92, it's a 9% chrome steel, and the CB2, it's the cast steel counterpart. And since they don't have the same mechanical properties, there's another buttering layer applied to the CB2 steel in order to fit them better together. And there's a weld material in between, 3 heat affected zones, and these are, as already said, selected into 3 subzones. So we have a total of 13 different materials for what we fitted literature data, just in order to get an idea of what error we will obtain when we are using the methods like abacus or the ASTME solutions. In order to get an idea whether these or how these methods compare, I checked 3 different models. So for the first model, I just used one material. So it's a homogeneous specimen where all methods to obtain the C star integral are strictly applicable. But the second one, the second one in the middle, there's the Norton exponent constant. So as you can see, we have only parallel lines in the Norton plot, and so it's the best possible option to use the ASTME standard formula, since there are only one exponent can be introduced. And the third one, we've just fitted the data set, and each data set got its own Norton model parameter set. And as you can see, we have a large variety in slopes as well as in y-axis differences. And this translates, if we have such an inhomogeneous specimen, to an inhomogeneous stress field. So as you can see here, there's the mesos stresses for a time step of, I think it was 15,000 hours of testing for the latest material data set described. So over these boundaries, there are discontinuities in stresses, and the whole specimen, as you can see, is deformed a bit unsymmetric. And if we're looking at the C star integral, so on the left-hand side, you can see the results for the homogeneous specimen. The homogeneous specimen was as well calculated using the ASTM method, Abacus contour integrals, and the stress power methods. The results are all normalized to the stress power result. So you can see here the Abacus solution is extrapolated to radius 0, like described in the Abacus manual. These are all almost equal, so you can see the model itself works pretty well. Same for n equal for all materials, but if we are looking at the let's say best fit for the actual material data set, you can see there's an error in the order of 10–15% if you're using either the ASTME standard or the Abacus contour, or better area integral for calculating the C star integral. So in order to conclude, I just want to mention the bold point in order to have enough time for discussion. If you're disregarding the heat affected zone properties when you're calculating the star integral, you are getting inaccurate results, and therefore is quite some work to do in order to cope with these welding configurations. Thank you very much.